We'll work out another problem in this lesson. The problem is shown here along with the figure for the problem. In this problem, a 700 Newton man stands on the middle rung of a 300 Newton ladder. That is, the weight of the ladder AB is 300 Newtons, and this 300 Newtons acts at this point C, where a man of 700 Newtons weight stands on it. So the total weight that is acting here at point C is 700 plus 300 is 1000 Newtons, and this force acts vertically down. Further, we are assuming that the floor, that is the surface here, and the wall, that is the surface here, are perfectly smooth, and that the slipping of the ladder, if these are smooth, obviously the ladder AB will slip both at A and B, and that is prevented by a string DE. Okay, the end E of the string is tied to the corner of the wall, and the other end is tied at D. Okay, and the angle is defined by 30 degrees as shown here. In the position of equilibrium, we need to find what is the tension S in the string and what kind of reactions act here and here. That is, what is the magnitude of the reaction. So you have three unknowns. One is the tension in the string S. The second one is the reaction at A, RA. The third one is reaction at B, which we designate by RB. We know that because the floor here at point A, point of contact A, and the wall here at point of contact B is smooth, the reactions are perpendicular to the surfaces. So at A, the reaction goes vertically up. At B, the reaction goes horizontally to the left. Okay, so knowing these three forces, we need to draw the free body diagram of an object and write equations of equilibrium to find the three unknowns. Okay, very clearly we can see that the ladder touches all these three unknowns. It is touching the string, it is touching at RA, it is touching at RB. So we will be drawing free body diagram of the ladder. Okay, it will be very useful to draw the free body diagram as neatly as possible, and as far as possible maintaining the proportions very clearly. Let us try to do that here. Okay, this is the ladder in the inclined position as shown. Okay, let me try to show the wall here, vertical wall. Okay, and this is the horizontal floor. Okay, both meeting at point E. Okay, and then you have a force going from this point D to point E as shown here, and we are representing that force by S. Let me show it here that this force is S. Okay, and then you have a vertical force at C. Okay, that force is going down, and this force is the weight 1000 newtons. 700 newtons is the weight of the man, and 700 newtons is the weight of the man, 300 newtons is the weight of the ladder. So the total force is acting at C. Okay, we have seen that the reaction at the vertical wall as well as the horizontal floor is perpendicular to the surfaces. So this is reaction RA, and this is reaction RB. B. Okay, it's a good practice to show all the angles right away and find whatever unknowns are there and perform all kinds of calculations that we may require right in the beginning. Okay, let us say we will extend this down, meeting the string at a point which we may designate as P. Okay, from P draw a horizontal line. That horizontal line meets here at N. Okay, and then this point is M. Okay, when we designate very quickly, we can see PNEM is a rectangle, so that PM is equal to NE. Further, this angle is given to be 30 degrees here. So very quickly we can see quite a few things. Okay, we are given that this total dimension from here to here is 2 meters. Okay, and we are drawing a line parallel to the side BE passing through the midpoint C. So obviously this M better be the midpoint of AE. So this distance is 1 meter. Okay, and we can also see this angle is also 30 degrees. Okay, this angle will also be 30 degrees. Okay, we can compute two quantities. For example, in triangle PME, we have tan 30 degrees is equal to PM by ME. Okay, which implies the side PM, which is equal to side NE, is equal to side ME, we have already seen, is 1 meter, multiplied by tan 30 is 1 over root 3. Okay, having noted this and knowing that this distance, vertical distance, is 4 meters. Okay, and knowing that this distance is 1 over root 3. Okay, the distance NB, the vertical distance between NB, we can very quickly find. NB is 4 minus 1 over square root of 3, that is 3.42 meters. So this distance is 3.42 meters. Having seen all this, we'll try to write equations of equilibrium for this ladder. Equations of equilibrium. Since the ladder is in equilibrium, moments of all the sum of moments of all the forces about any point in the plane of this ladder must be equal to 0. So we begin with by writing sigma sum of moments about point E is equal to 0. That is, we are taking moments about this point E, moments of all the forces. Okay, because the string is passing through E, the force S does not contribute to any moment. Okay, so the only three forces that contribute to moment are RA, RB, and the 1000 Newton force. So we will write down one equation as, let us say, 1000 Newton force multiplied by its perpendicular distance from E, that is EM, which is 1. Okay, 1000 by 1, and we can see that it is creating an anti-clockwise moment, so it is positive. And the other moment is moment due to the force RB. Okay, this RB is also creating a counterclockwise moment, so we will use it with a positive sign, plus 4 times RB. I'm writing 4 times because the perpendicular distance from E to line of action of RB is 4 meters. Okay, and then there is other force RA. This force RA is creating a clockwise moment, so it is negative, and I take that negative onto the other side of the equal to sign to write for RB is equal to RA multiplied by the perpendicular distance from E to line of action of RA, that is 2. So you have an equation 1000 plus 4RB is equal to 2RA. Let us call it equation 1. We can write another equation of equilibrium as sum of moments about other point. Let us say we take moments about this point P. When you take moments about this point P, two forces do not contribute any moment. The weight W, it does not contribute any moment because it is passing through P. The force in the string S does not contribute any moment about point P because this S is also passing through P. Okay, so two forces are eliminated. When you take sigma MP is equal to 0, you get another equation. That equation is RA is one force. Okay, RA is contributing a clockwise moment which is negative, and RB is creating a counterclockwise moment which is positive. So this RA multiplied by the moment arm from P to A is RA multiplied by MA should be equal to RB multiplied by its moment arm, that is the perpendicular distance from P to RB, which is equal to NB. Okay, we already know these distances. MA is equal to 1 meter, so RA is equal to NB is 3.42 multiplied by RB. I'm sorry, I think I should be using lowercase a at all places. RA, okay, I think I used lowercase a at all places. This is equation 2. So we get, substituting two in 1, we get, okay, you have 1000 plus 4RB is equal to 2RA, and RA is 3.42 RB. So you have 6.84 RB. Solving, we can get RB as 351.62 newtons. Therefore, RA is 3.42 RB is equal to, if you substitute that number, you will get 1 203.23 newtons. So we found two of the unknowns. We found what is Ra, we found what is Rb by using two equations of equilibrium. One equation of equilibrium we have written is sigma m is equal to me is equal to 0. The other one is sigma m p is equal to 0. To find the other unknown, we can take moments about any one other point which is not collinear with E and P, and then take the moments about that point. Fortunately, we have a simpler approach. We can very quickly identify, let us say, x-axis to be going this way and y-axis to be going this way. Let me mark them. Let us say this is x-axis. Let us say this is y-axis. We can sum up all the forces along x-axis and equate it to 0. Okay. You have only two forces which contribute moment about x-axis. This W does not contribute any moment because it is any component along x-axis. This W does not contribute any component along x-axis. Then similarly RA does not contribute any component along x-axis because both RA and W, they are perpendicular to x-axis. There are only two forces that contribute components along x-axis. This force S contributes a positive component, RB contributes negative component. So we will write the component of RB along x-axis is minus RB because it is pointed towards the negative x-axis. You can see that the direction of RB is going opposite to that of x-axis. That is why we used negative. The other component along x-axis comes from the force S, and this is positive. S cos 30 degrees is equal to 0, which implies your force S is equal to it comes out to be 406.02 newtons. So you list your answers as your RA is equal to 1203.23 newtons. You have RB is 351.62 newtons, and you have S is equal to 406.02 newtons. That will be your answer, and you will show it in a box. We'll try to work through a couple of more problems in subsequent lessons.